In this video we are going to see that how we can calculate the heat transfer through different mechanism. So let's first of all discuss the heat transfer by radiations. So the heat transfer through the radiation depends upon the area and is given by this expression 5.7 into 10 raised power minus 8 into E into A Ts power 4 minus Ta power 4. So what is this P radiate? That is the radiated power in watts from your device. So let's suppose that you have this device or some surface. From here the heat can be radiated into the environment. Environment temperature is, let's suppose, Ta, and the surface temperature of this material is Ts, and A is the cross sectional area of this surface, which is basically radiating the heat, and E is the emissivity of the surface. So if you know the ambient temperature, surface temperature, emissivity of the surface and the surface area, you can find out how much power will be radiated. The value of E for the black oxidized aluminum heat sink is 0.9. So if I use this value of the E in equation A, that is this equation, so we can write down this equation like this as shown in the equation B. So radiated power can be expressed with the help of this equation. Now, as we have discussed in one of our previous lecture, that the thermal resistance R theta is equal to delta T over PD. Delta T is the temperature difference and PD is the heat flow in terms of watt. So using that, I can say that theta radiated thermal resistance for the radiated heat is delta T over the power that is radiated. So delta T divided by 5.1 into Ts by 100 power 4 minus Ta by 100 power 4. That is from this equation. Okay. So now if we have the sink surface temperature of 120 degrees centigrade, that is 393 Kelvin, and the ambient temperature of 20 degrees centigrade, that is 293 Kelvin. So thermal resistance R theta radian is given by this equation. Just area is unknown if the temperature difference is of 100 degrees centigrade. So with the help of this equation you can find out the thermal resistance when the heat is being radiated in the from the surface to the environment. Okay, now let's go through this example. Let's suppose that we have a cube of the material, and that is of black oxidized material, right? So if the each side is of 100 centimeter and there is the temperature difference of 100 degrees centigrade between the surface and the ambient, so what will be the thermal resistance of this material? So that can be calculated using the expression that we defined above. R theta is equal to 0.12 by 6 into A, where A is the area. Why 6? Because there are 6 sides. One side is this one, Let's suppose that let's write it the right side. This one is the left side, top side, bottom side, front side, and the back side. There are 6 surfaces. So because of that, we are multiplying this area with the 6, because we are calculating the area of one surface. So area of one surface is 0.1 square, because the length in terms of centimeter is 10 centimeter, and that is equivalent to 0.1 meter. So 6 into 0.1 square. So R theta radiated means the thermal resistance for the radiated heat will be 2 degrees centigrade per watt. Now let's look at the heat transfer by the convection process. The power that is dissipated or transferred is given with the help of this equation. That is 1.34 into area into delta T power 1.25 divided by d vertical. So we have considered a sheet, you can say, whose vertical height is d vertical and width is this W, and the thickness is very small. And we are basically considering the heat dissipated by the convection process. So air is going to flow in the surrounding of this sheet and will take away the heat from its surface. So that depends upon the cross-sectional area of this sheet and the vertical height of the body in meters. So if I write this equation in terms of R theta, that is thermal resistance, R theta is equal to delta T by PD. So delta T dividing by this PD is basically, over here we are discussing the convection, so it is P convection, the power transferred by the convection process. So delta T by P convection, so taking that value, so our equation will reduce to our equation for the thermal resistance will be this one. Now for the temperature difference of, let's suppose, 100 degrees centigrade and the vertical height of 10 centimeter, the thermal resistance for the convection process will be 0.13 by area degree centigrade per watt. So let's suppose that we have the plate whose height is 10 centimeter and whose width is 30 centimeter, and we want to calculate its thermal resistance for the convection process. So taking this equation, R theta convection will be equal to 1 by 3.4. Why this 2 is there? Because we have two sides of this one. Let me call this is side 1 and the other side will be side 2. Surface area will be double. So 2 is representing the number of side, and height is 10 centimeter, width is 30 centimeter. So 10 and 30. So its thermal resistance will be 2.2 degrees centigrade per watt. Now both of the process can take place simultaneously. The heat transfer can be through radiation and can be through convection. So let's suppose that this is the surface and radiation process is taking some heat, convection process is taking some heat. So these two resistances are there, R theta radiation, R theta convection. So both of them are dissipating the heat into the ambient whose temperature is TA. So we can say that these two processes are working in parallel. So when they are working in parallel, what will be the net thermal resistance from sink to the air or from the surface to the air? So this is r theta SA. So that will be the parallel combination of these two resistances. So r theta surface to air, that will be equal to r theta for convection, that is in parallel to r theta for radiation. So if we take their parallel combination, we will get this equation. So that will be the total thermal resistance when the convection as well as the radiation process is going to take place. Now some part gives you more radiation as compared to the other part of the surface. Let's consider the case of the cube. If we have the cube, the surface can radiate more heat as compared to the bottom side if it is placed over something. So the radiation can be more from the surface. So usually for a cube, the upper surface radiates 15 to 25% more heat as compared to bottom side, or if we compare it with the vertical surface. So we need some correction factors for a good estimate of the thermal resistance. Okay. So now let's discuss another example through which more concepts will be clear. Let's suppose that we have this heat sink. The width is 0.115 meter, the height is 0.07 meter, this is height, this is width, and the depth is 0.63 meter. And you can see number of fins over here. To increase the surface area, so now let's calculate the effective area for the radiation. Effective area for the radiation will be for this heat sink will be the four sides. Which four sides? One is this front one, considering the flat surface. Similarly, its equivalent will be there on the other side and this side. And similarly, its equivalent will be there over here. So there are four sides. So we will be calculating the total surface area that will be used for this for the radiation. So effective area for radiation is 2 multiplied by 0.015 into 0.75. So we are calculating the area of this surface, 0.075 multiplied by 0.115. So you will get the area of this surface. Okay. Sorry, by mistake it is written 0.75 over here. It is basically 0.075. Then taking the side surfaces, these one. So the height is 0.075 and the width is 0.063. So the area of the side surfaces, the total area will be 0.0267 meters square. So r theta for radiation, if the temperature difference is of 100 degrees centigrade from the surface to the ambient or surface to the air, we have seen is given by this equation, 0.12 by area. So its thermal resistance will be 4.5 degrees centigrade per watt. For different temperatures difference, you will have to calculate this factor from the expression that is discussed above. Now if I look at this second diagram, diagram B, the distance between two fins is 9 mm. So now let's calculate the effective area for the convection. We have seen that for the convection, the r theta is given by this equation 1 by 1.34 into area into d vertical by delta t power 1 by 4. But what is this? This is basically the reduction factor, because when the number of fins are increased, if the air is going to flow over here, so air contact with its surface is basically gets reduced. So it affects the thermal resistance for the convection. So that factor is over here at what will be the effect over thermal resistance because of convection process. Now let's calculate the effective area. First of all, so for that, look at very carefully. We have this surface, this one, and we have its back side as well. So if I consider it a plate like this, area from this side and the area from this side, so whatever is the surface area of this one, and if I calculate it numerically, it is 0.063 multiplied by 0.075. So this is the surface area of one side, and the other side will be of equal area. And how many such are there? 1, 2, 3, 4, 5, 6, 7, 8. 8 fins. So total area will be 16 multiplied by this surface area. So that you can see over here, 16 multiplied by A1 plus this one, the front side, this surface and the back side surface. So 2 multiplied by the area of one surface, right? So 2 into 0.75 into 0.092 plus 16 into 0.063 into 0.075, looking at the dimensions over here. Okay, so we can find out the total area, that is 0.089 meters square, the effective area. The reduction factor for the convection area to the naturally cooled heat sink with cooling fins separation less than 25 meter is given in this graph. So we can see for 9 mm distance between the cooling fins, the correction factor is 0.78. So taking this is equal to 0.78 and then using over here in this equation the numerical values, we can find out the r theta for this convection process, that will be 1.8 degrees centigrade per watt. And now we can look at the combined effect. We have calculated the r theta for convection process, r theta for the radiation process. So both of them are going to take place in parallel. So net thermal resistance will be 4.5 multiplied by 1.8 divided by 4.5 plus 1.8. That is the parallel combination of r theta for convection with r theta for radiation. So this comes out to be 1.8 degrees centigrade per watt. So total thermal resistance for convection and radiation process will be this one. What was that? 1.3 degrees centigrade per watt. So 1.3 degrees centigrade per watt is the total thermal resistance of heat sink for both of the processes, conduction as well as convection. Okay, so what we have discussed in this video, if I summarize, we have discussed the expression for the heat dissipated through the convection, then we have seen the expression for the heat that is dissipated through the radiation, and then we have seen how we can find out the effective area for the convection and the conduction process, for the convection and radiation process, and how we can calculate the thermal resistance of the heat sink. Okay, so that's all from this video. Thank you very much.